Here I have a guest I'm super duper excited to introduce to you all. His name is Professor Mike Burkart. He's one of the co-founders of a company called Algenesis that does some wonderful research that really positively impacts our environment around us. And also recently just got promoted to the chair of the chemistry department. So congratulations.
Thank you. Congratulations, condolences, they're both in order.
Condolences.
Yeah.
Oh man, is your schedule really?
Oh yeah, as I was coming in, I said I'm chronically late. I'm always on time for things normally, but these days
it's really
I just can't because everything. I got just meetings back to back to back. I can't walk down the hall without somebody saying, "Hey, Mike, I need to talk to you about something." Wow. It's fun. It's just It's.
I mean, like that must be challenging, But hopefully you can make time for yourself.
I try.
Well.
I've been trying to fit that in.
One of the things I was super interested in is now that you're at this chair position, how your understanding of the university has evolved and progressed as you've adopted more responsibility.
Sure. Well, it's been interesting, right? So I've been here now 20 years. I came here straight out of a postdoc. And so, I had almost no teaching experience. I didn't know really how to mentor people. I didn't know how to write grants. You start as an assistant professor and you're just kind of thrown into this environment where you've got to wear a bunch of hats. And so you kind of go through stages of learning all of these skills. And part of that, as you say, is learning about the university, right? And learning about, because this place is enormous.
It's huge.
Right? And it's actually twice the size it was when I started. Right? So we've actually got double the number of undergraduates, right? We're almost up to 45,000.
It probably doesn't look anything like when you first came here.
It's certainly very, very different. There's way more buildings and a lot, and it's most of it's good, right? I would say the biggest downside is that it's just gotten a lot more bureaucratic, right? Where now you've got to fill out a form to get anything done, and you can't just walk into someone's office and ask for something. But then, the other thing that you point out is, like now I'm part of the administration, and I wasn't before, right? I was just a faculty member.
Yeah.
And so you do get a different perspective about things, and I think you start to see how solving problems is a lot more complicated than maybe you assumed it was, right?
Yeah.
And part of that is also the bureaucracy. But anyway, it's been going. I've only been doing this for about 2 months now.
2 months, yeah.
So I'm still learning.
Still learning. I love to hear that. Yeah, I'm glad because I want to continue to learn throughout the rest of my professional career. And sometimes I don't know. I feel like I don't hear that too often. People say that they're still learning, even when they're in a position like yours.
Old. Yeah. Well, I would say that's really why I decided to become an academic, is because I kind of have that luxury now, is that I'm always learning new things. And, the really amazing thing about doing academic research is in my lab, I'm doing what I think is awesome. Right?
Yeah.
And I can change that, right?
Yeah.
Now I've got to go find funds to do that research, right? So I got to write grants and I do that process. But it's just been amazing, and we'll talk about kind of the research side of things and how that's transformed over the years. But I'm always learning new things, right?
Yeah.
And I mean, maybe I get bored easily, but I'm always really stretching my comfort level with science, and it's important to me that I do things that I know nothing about, because I really like that in science. I'm really excited about that.
Yeah, well, that kind of makes the two of us with this podcasting thing.
There you go. Right? So that's a perfect example.
It's so cool. So I mentioned you're one of the co-founders of Algenesis, and I really like the mission that you have at Algenesis. The research that you have is so fascinating, and the articles you've sent me particularly show how resourceful Algenesis is as a company when it comes to, what can we use this part of the algae for example. I would love to ask you, what do you think distinguishes Algenesis from other material science companies, you know?
So Algenesis is kind of a funny beast in terms of as a materials company, because we really are a direct spin out of research that's happening at UCSD. And what's very fun about it is that we really have a pipeline that's going from our academic research in our laboratory at UCSD, you know, the students and postdocs are doing, directly into the company.
Yeah.
So we can do fundamental research to figure out really basic things, and then we just pitch that over the fence to the guys at Algenesis. And by the way, like, we have meetings together every week, so this stuff happens very seamlessly. So that allows then us to really rapidly go from fundamental science to a product.
It's so cool.
Right? And in my other research in my lab, we do a fair amount of stuff that's like biomedical. Like we work on natural products, and some of them are you know, could potentially be turned into drugs and anti-cancer molecules, antibiotics. And that process takes decades and decades, right? I mean, to get a drug through clinical trials and into you know, being sold to people, that takes 20 years, right? So this is a very different experience, right? And really exciting.
Yeah, it is super exciting. And recently you all, I mean, not sure, was it last year you dropped the Reef, the Blue View? Is that what they were called? Forgive me. What was the
Blue View is the brand, right?
Brand,
that's kind of like the, you know, the Nike or the Adidas. And we trademarked the material. So we're making these polyurethane materials that are renewable and biodegradable. And so that's called Soleic. So that's kind of like Gore-Tex, right? Gore-Tex, you see the little Gore-Tex brand on a shoe that you buy from some other company. Yeah. That's the branded material, right? And then, so we started a collaboration with Reef. So we developed our shoe, or just these slip-on shoes that are our own. So that's Blue View. And then we have a collaboration with Reef to make flip-flops. And so what that's going to say is, it's going to say like Reef by Soleic, or you know, something Reef, like that. And so they'll be co-branded with Reef.
Okay. Funny question. How'd you come up with the name Soleic?
So we sat around and brainstormed, and we all threw out ideas, and we kind of liked the idea sol coming from the sun. Oh yeah. And oleic is like kind of about, I mean, like oleic really has to do with like oils. Okay. Right. Yeah. Because we're using algae oil to make this. So
that's cool.
Oil from the sun.
Yeah. And sol's also like your feet.
There you go. Yeah.
There's so many entendres here. I was wondering, I was like, I think this dropped before ChatGPT blew up, so maybe...
It did. Well, it's funny because...
maybe ChatGPT could help.
Well, also like for designing logos and all of that.
Yeah, there's just huge.
Also AI, right?
Yeah.
And that's very recent.
Okay. Cool. One of the other relatively recent articles you sent me was detailing a new method for producing one of the precursors to these polyurethanes. The industrial standard that is still used today, I believe, uses phosgene as one of the chemicals to produce the precursors for these plastics, right? Yeah. And your lab did research on this. What was going on in your head when you decided to embark on this research? What were you thinking? Did you just like think, oh, okay, well, phosgene is hazardous and we're trying to make our product not require that huge capital that is necessary to use phosgene? What was going on?
I would say there was part of that, but it's a lot deeper than that. So polyurethanes, just to step back, polyurethanes are made by mixing a polyol and a diisocyanate. So polyols are just molecules that have alcohols on them. They can have as few as 2 alcohols or as many as dozens. And diisocyanates react with those out. So the isocyanate portion reacts with the alcohol and creates a urethane bond or a carbamate bond in organic chemistry. And you have a diisocyanate, so a molecule has two of those isocyanates, and that does the cross-linking. So that's how all polyurethanes are made. And what we love about polyurethanes is they're extremely diverse. So they're in everything from, for example, we've got rigid foams like surfboards, we've got flexible foams like shoe soles and cushions. You have polyurethane adhesives. You've got thermoplastics like a cell phone case. You've got paints and coatings.
Probably this stuff right here too.
That's definitely So it's all over the place, right? And what's really interesting is you change the identity of the polyol, or you change the identity of the isocyanate, and you can formulate for these different applications. And that's why we really like them. Number one, because they're very versatile, and number two, because you can make them biodegradable. So, and we kind of figured that out by saying, okay, well, what can organisms biodegrade, and how do we go and try to make bonds that can be cleaved by these enzymes? Right? So that's kind of where we began with that. So when we started going down then the process of making our shoe sole foam, we just decided to start with the polyol side, because we knew that it seemed pretty obvious that we could take the algae oils that we were making, we could break them into smaller pieces. In this case, we would ozonolize them to make diacids, and then we would build those up to make the polyols. But we also knew that if we didn't touch the diisocyanate side, we were never going to be able to get 100% renewable materials, right? And we knew we needed to do that. Now, as you mentioned, diisocyanates are, through chemical manufacturing, it uses phosgene. So phosgene is, as you said, a very dangerous chemical. It actually used to be a chemical warfare agent in World War I. More people died in World War I from phosgene than bombs.
So
than nasty stuff.
Gas.
It's one of those types of gases. So it's very dangerous. Like if you want to have an industrial facility, it costs billions of dollars just for all the safety equipment. In fact, it's mostly robotic. Like they actually generate the phosgene on site and they consume it. And anyway, so as a result, there are very few diisocyanates available. There's a handful of them, maybe like 6 that are commonly available. And that's the reason. Now, the precursor to that is a diamine. So molecules that have two nitrogens on them, right? And those nitrogens react with the phosgene to make the diisocyanates.
Certainly.
So what we were trying to do is say, okay, how can we find a biomolecule, right, some metabolite, and find a route to get to the diisocyanate. And this is what's cool about this research. It's highly interdisciplinary, right? We have to understand the metabolism of the algae. We've got to know what types of molecules we can actually isolate and purify. And then we have to think about how we do the chemistry to get them to make monomers. And we got to know what monomers are going to be valuable and useful for making the polymer. So there's a whole lot of kind of parts to this that we have to understand. So when you think about where energy is stored in an organism, where the hydrocarbons are put, there's really 2 different types of biomolecules. You've got lipids, so fats and oils, right? I got a good storage of that going on right here. And carbohydrates is the other one, so starches. Right? You think about cornstarch or potatoes, right? That's starch. That's where organisms store their energy. And that is going to be the highest, amount of biomaterial that you can use for whatever you want to do with it, right?
Cool.
There's no nitrogens in either of those. Right?
Yeah.
So if you now want to get a nitrogen on those types of molecules, you either need, so biologically, there's nitrogens in amino acids and proteins, and there's nitrogens in nucleotides, right? DNA and RNA. But trying to now think about somehow taking that metabolic pathway and sticking a nitrogen, and not just one, but 2 nitrogens, that is actually really hard to do. And you might be able to come up with this synthetic biology approach to it, but that's going to be a 10-year project at least, right? And so we started thinking, okay, how can we put those nitrogens on later, right? Can we pull the oil out of the algae. Can we make some precursor that then we can stick those nitrogens on later? And so that's kind of how we came about this process. So we do what's called a courteous rearrangement. And to do the courteous rearrangement, you make an acyl azide.
Yeah.
Right? So an acyl means it has a carbonyl, carbon, oxygen, and azide, you've got 3 nitrogens.
Yep. Three of them.
And you heat that up, and it actually does a rearrangement where one of the nitrogens inserts between the carbon and the oxygen, between the carbon and the carbon before it, and then you lose nitrogen gas into. So that's actually been known. This chemistry has been known for a long, long time.
Okay.
The problem is no one ever used it because the acyl azide is explosive.
Yeah.
Right? It's very dangerous.
Yeah.
So you wouldn't want to have a pile of it here
at all,
because it would be, you might lose your hands.
Yeah.
So that's why no one ever touched it. And so people knew this chemistry, but nobody
no one wanted to mess around with it.
And so we thought maybe we could come up with a way to start using it, but where we generate that intermediate, but only in situ, right? And very small amounts. And we started using what's called flow chemistry. And so flow chemistry is a process where rather than using flasks or reactors, you're actually using pumps and tubing. And so you pump stuff through the tubing and they meet together and react. And so that way we came up with a route where we can make that unstable acyl azide and immediately take it on to the next step. So you're never isolating it, you're never having it in a high concentration. It immediately goes to the next step, and then we can collect the product. So we kind of put that together, and I had a super talented postdoc named An Feng who had demonstrated this. And he rolled it out. I think he had like 20 or 25 different example molecules that he did it to.
Yeah.
And
yields were good.
It actually has been a big success, not only for us, but that paper's getting cited, people are realizing, hey, this is a real potential. So here's what's cool about that. Remember this thing where phosgene can only happen at certain locations, right?
Yeah.
You can now take this chemistry and you can take it to a desert island, right? And if you have a diacid and you've got the reagents, you can make the precursors to make polyurethane. So that's now what we call distributive, right? It democratizes this science, right? So that really, granted, it's a little complex. You gotta know what you're doing, but anybody could really do this now. You don't have to have $1 billion factory to make this happen. And we haven't, that hasn't yet taken off. We don't have people making diisocyanates in their garage yet, but it could happen, right? And so I'm really excited about that.
Yeah.
It also democratizes, if you can say that word, the inputs, right? So you could now make these molecules from any of a variety of starting materials. Yeah. Right? And that includes renewable materials, that stuff we get from algae. And so I think that there's now the possibility that you could make, because you're no longer confined to just the 5 that you can buy from the Aldrich catalog, you could make any of, thousands of different potential starting materials. We can now maybe make materials that have completely new properties, completely new applications. So I'm excited about that too.
That is super exciting. And it made me realize, I'm just about to get my master's degree. Just got 2 more of the ACS exams left. And I'm really reflecting on it as I'm studying for these last exams. And we don't learn anything about flow chemistry.
No.
At all.
So actually I'm talking with...
And you're the chair, so you know how important it is, right?
I know. So I
got to do something for the future, Mike.
So I've now written 4 proposals to the NSF with Chaim Weissman to try to bring this into our instruction. Flow chemistry. And it hasn't been funded, right? So we're going to keep trying. But I really want to do this. So Chaim is a teaching faculty in our department, and we want to actually bring this in.
A great one too, might I add.
Fantastic. And so we want to bring him in, bring it into 43B, right? 43A or
so that'd be the second quarter of organic
the
chemistry.
OChem lab.
Yeah.
right? And so we may even make diisocyanates. I don't know yet, but you know, it's definitely possible that we could do that. So we want to bring flow chemistry because I honestly think that it is the future. I mean, right now, particularly with any process that is very high volume. So apparently, maybe about, I don't know, 8-10 years ago, there was this huge explosion in a city in China. Was it Guangzhou? Maybe it was Guangzhou, where there's a lot of chemical manufacturing. An entire plant went up. It basically destroyed an entire part of the city. And after that, China implemented that any process that's making more than 4 tons of anything has to use flow chemistry.
No way.
Just for the safety elements of it, right?
Yeah.
Because what's cool about flow is it's one of those things that you're generating continually, right? So you can generate this from 9 to 5 or 24/7, but it's small amounts, little by little, building it up, and you can always just turn it off, right? You're not doing enormous, giant, huge reactors. Granted, you may be generating a product in bulk. But what this does is it allows you to do these types of dangerous steps or things that could be potentially dangerous, and you really increase the safety levels.
That's so cool. And also the amount of supervision you need to give to the reactions as well, right?
Absolutely. I mean, you don't want to leave them completely unsupervised, but you can definitely set it up. Like once you've optimized the system and it's going, you just let it go and you can do other things, which is nice.
That's great. Yeah. This is a nice segue into other proposals you have now that you're a chair position. What are you trying to implement?
In the department?
No, let's talk about the chemistry.
Sure.
Yeah.
Well, so, we're continuing to work on materials. We've been continuing to try to improve the flow process, really incorporate flow into as many different parts of this value chain as we can. And the other thing that's kind of cool about flow is that you can take processes that have multiple steps, where you would actually isolate intermediates along the way and put them all into one continuous system, right? So that is also something that's exciting.
Okay. Something I was thinking about, I mean, I don't know much about flow chemistry. I researched it a little bit before this. It seems closer to chemical engineering than chemistry because you're dealing with flow rates as your stoichiometric equivalents as opposed to just concentrations. Yeah. So maybe it's a little bit more advanced. Is that what you're thinking? That's how I feel. I don't know.
So yes and no, right? I mean, chemical engineering as a discipline, oftentimes those people are concerned about actually, building giant facilities. I should mention, flow chemistry actually is what's done with petroleum refining just because of the sheer volumes. It's been done. They've used flow chemistry for decades and decades, right? Yeah. But things like, pharmaceutical manufacturing, materials manufacturing, these kind of mid-volume areas have all been batch up until now. So I think this is where the transformation is going to happen. But here's what's, you mentioned education. What's really interesting and fun about flow chemistry is that, if you take a reaction and that's working in flow chemistry and you want to change it, let's say you want to up the rate, right, from 1 mil per minute to 5 mils per minute. Well, you actually have to now go and optimize that whole process, right? You can't just turn the switch up, right? You have reactors that are a certain size, certain temperature, and if you crank up the temperature, well, it may go too fast through that reactor and not go to completion. So what that means is you actually really need to understand the chemistry, right? Deeply, and you need to understand reaction kinetics. So this is actually a really great way to teach organic chemistry because it's really easy to show that to someone by all you got to do is turn a knob and turn the flow rate up, right? So I see this as an opportunity to understand fundamental chemistry and and really teach that stuff in a kind of real world situation.
Okay.
So you're right. It does seem like engineering because we're now using computers and
yeah.
pumps and stuff.
Yeah.
But that's okay, right? I
That's
mean,
great.
Science changes over time. Right? We don't have to run the same reactions that we were doing for undergraduates 100 years ago.
Yeah, 100%. Something I talked to you last time we spoke. I asked you about natural product biosynthesis. So right there, you have some green tea. Most people, they'll probably look at the green tea and they'll think, oh, it tastes nice. It's got tea in it. Your understanding is, I feel like, would be a lot more nuanced and definitely chemical. You'll think, oh, this green tea has aromatic compounds that are present in it that contribute highly to its flavor. And these aromatic compounds were synthesized by the plant. And the manner in which the plant synthesizes the aromatic compounds is incredibly complicated and can also be changed, manipulated, and studied intensely. And that's what you do in some ways. Shape,
that is what I do. And I teach it, right?
Yeah.
This morning, so for 18 years, I taught a class in natural products, and we talk about how caffeine is biosynthesized. We talk about how these different pigments are made in plants, right? The different alkaloids.
Yeah.
And you're right. I absolutely think about things on a molecular level.
Yeah.
I'm also thinking about the plastic that
plastic too.
This tea is in.
It just doesn't turn off.
How the molecular connections and whether or not this thing is biodegradable or whether or not it's recyclable. And
what do you think? Is it?
I think this is not recyclable, but it is not biodegradable, but it is probably recyclable. Yeah, it's got the little recycling logo on it.
And when I took your class, I really appreciated it because I could tell not only did you want to educate us about how this works, but you also wanted to entertain us. You'd wait to tell us. You'd wait to tell us the identity of the molecule for which you were showing the natural, but the biosynthetic pathway.
Right. You're thinking about cocaine, aren't you?
Well, that remains to be determined. But I think it was LSD. LSD was the one where I was like, wow, this is crazy. And how did you approach natural product biosynthesis? What was it that made you so passionate about it?
I guess I'll first say what attracted me to chemistry was really the knowledge that I was gaining about the molecules that were around me. I'd open up my medicine cabinet and you get some prescription medications that have that really long paper thing with little tiny print on it.
Yeah.
And you look at the structure of the molecule, and I would, just taking sophomore organic chemistry, I could be like, oh wow, like I know how these bonds could be made, and I could propose making this molecule. And of course, I would sit and think to myself, well, how would I make these illegal molecules? Right? How's this being made in these drug factories in Mexico?
Yeah.
So I just found that just intellectually really fascinating. And that's kind of what got me excited about chemistry in the first place.
Yeah.
And then it wasn't really until later that I learned I took a biochemistry class and I learned about the organic chemistry of life. And that just, I guess for so long I had separated these things. Chemistry is this thing, and biology is this thing. And when I suddenly realized that, this was an artificial division that we've made, and nature is doing really exquisite organic chemistry, and that's when I got excited about that. And you look at these natural products and you see these crazy molecules that have halogens in them and heterocycles and aromatics and all this kind of stuff. So that really, trying to understand how nature puts these molecules together is really the thing that caught my passion. And it caught it, when I was in grad school is when I learned about that stuff, and that's really what motivated me to do academic research. But when I teach this class, you're right. I want to entertain people, but I want you to see how this stuff is all around you.
Yeah.
Right? And I try to bring up examples. You know, we use this textbook that's not a textbook. It's really more of a reference guide. But I try to pick out molecules in it to teach from that we're familiar with, right? Flavors and fragrances that maybe you had for breakfast this morning.
Yeah.
And this is how that plant makes it.
Yeah.
On Tuesday, I was talking about sterile biosynthesis.
Okay.
And we talked a little bit about the marker.
Sterols? I forget. Which ones?
Cholesterol.
Oh, cholesterols.
And other types of steroids.
Okay, sure.
And we talked about the marker process and how you might remember my story about Russell Marker, who figured out.
It rings a bell.
He went down to Mexico.
Yeah.
And found out that this Mexican yam down in Orizaba, Mexico, made this precursor, and he figured out a synthetic pathway to make it. Right?
Yeah.
And that's what got us the birth control pill, right? That's also what got us this molecule mifepristol that's been in the news lately because it's used as an abortifacient for chemical-induced abortions, right? So I try to bring up things that people are thinking about or reading about, and say, look, this is actually really interesting stuff that's happening right as we speak.
Okay. And I really appreciate you for doing that because that made me so much more engaged in class, and that is super meaningful. So thank you.
Good.
Last thing I have that I wanted to ask you about, and I have asked you something along these lines in the past, is I took this class called Chem 151. It's called Molecules That Changed Society.
Yeah.
And I really, really love this class because it's like what you said, except on steroids, pun intended. So we go through all these molecules and all these discoveries, and I'm thinking to myself, this is awesome. But I've noticed that they kind of like slowed down in terms of, for example, like we discovered aspirin from the willow bark tree, but that was like hundreds of years ago.
1893?
And like these discoveries seem to have happened like so long ago, and now it seems like natural sources are not it doesn't seem like we're making all these like haphazard coincidental discoveries of like molecules that are impacting society now it's all just like trying to like push this, as you said, like push the envelope a little bit, and the discovery seems to have changed. Would you agree?
Yes. So I guess probably the best way to say is all the low-hanging fruit's been picked.
All the low-hanging fruit's been picked.
Now, that doesn't mean there's not more fruit on that tree, but you got to reach a little bit higher for it. And this is the curse of natural products. In fact, there were dozens of pharmaceutical companies that had active natural product programs in them, and most of them got canceled, right? And they moved totally away from natural products and towards high throughput screening, fully medicinal chemistry based. And you go and you look at molecules that get approved through by the FDA, and most of these are unnatural, right? And they've been designed for active sites of enzymes and very carefully screened or designed. And by the way, I don't have any problem with that, right? I'm still an organic chemist by training, and I think a lot about drug discovery. But at the same time, nature, has had the benefit of billions of years to find molecules that we say are privileged, right? That evolution has discovered these. So I guess what I mean to say is there's still interesting and important stuff out there. But you're right in that you just don't see it all that often. Yeah. The other thing that I could say is that you would never get aspirin through clinical trials today, right? It's too toxic.
Oh, really?
Oh, yeah. Like aspirin is actually pretty dangerous.
Really?
At certain amounts, and so it would be really hard because of all aspirin doesn't just do one thing in your body, right? It's doing all kinds of stuff.
Yeah. So wait, why are we still ingesting it?
Well,
we stopped?
We're kind of not.
Oh, we're done?
When's the last time you took aspirin, right? You'll take Tylenol or ibuprofen.
I'll take your
instead.
word for it. Yeah, we take Tylenol and ibuprofen. Yeah.
Right? I haven't taken aspirin in a while. Anyway, all that being said, the bar is now really high for discovering new drugs, and in terms of safety, toxicity, bioavailability, all these things. And keep in mind, these molecules are never made by their producing organism to go into the human body. Right?
True.
So a lot of times we'll find a molecule that has this really fantastic activity, and then we have to modify it so that it works better in the human body. On top of that, you actually can't patent a natural product anymore. So if you go out and discover something that's made by some tree, you can't patent it. You used to be able to, but you can't anymore. So now you really have to take that natural product and somehow modify it and make it better in order to actually make a drug out of it. So there's a lot of ramifications to this, and it's just gotten harder. It's still super interesting, and I'm working on a project now, so I actually have another company we haven't talked about, but it's called Aspera Biomedicines.
Aspera Biomedicines?
Yeah, where we're working on a natural product class that we've been working on my lab for 17 years, and we found an analog that has really potent activity against cancer, specifically against leukemia, and so we're about to get this into clinical trials.
Wow.
But it's a very long process.
It's
also a 30-step synthesis. So so there's a lot that goes into that.
There's so much. I cannot imagine.
But yeah, and that's all based on a really exciting natural product that we found targets the spliceosome and has really potent and selective activity against cancer. So things are still coming.
Okay, cool.
It's just maybe it's not so obvious.
All right, sweet. I lied. There's one more thing I would like to talk to you about. And this is structural color.
Oh, yeah.
You told me that melanin operates in a little bit of a funny way.
Yeah.
And you research melanin, right?
That's right. Yeah.
How does melanin work?
Okay. So we still kind of don't know, but we know a lot more now.
Okay.
So melanin is this fascinating polymer that is insoluble in everything, and it is a polymer that's based on
everything.
Well, so it's comes from tyrosine originally.
Okay, sure.
Right. So, excuse me. Well, it can be phenylalanine or tyrosine. Either of those. Phenylalanine will get oxidized.
Okay.
So it goes through this process called the Raper-Mason pathway to get to these cyclized forms of tyrosine that then polymerize.
Okay, cool.
And they polymerize by radical mechanisms. And the polymers are completely insoluble. They crash out of solution.
Yep.
They're not soluble in water. They're not soluble in organic solvents.
Okay.
And so we actually kind of don't know what melanin is because we don't have any spectroscopic methods to actually determine, it's not crystalline, so we can't do X-ray diffractometry. So what's funny is that we know what the precursors are.
Yeah.
But we don't know what the final product is. And one thing my lab has been doing is looking at the biosynthetic pathway, trying to elucidate or predict what we think the structure is. And then we've been doing solid state NMR on the insoluble stuff.
Okay, sure.
And comparing the starting materials to the products and trying to figure out what we think the structure is.
It's so interesting how you're using two different routes to get to this final structure.
Yeah.
I feel like there's a big misconception that as chemists, we just know everything about the structure.
Well, on TV, right? You just put it in a machine and the 3D structure
it's like,
pops up.
no, like we don't. Like, we just are very certain that it is this type. It is this type.
And not that.
And not that. And melanin is a good example of that.
It is. So just to say then, what melanin has a lot of different functions. We know that it is protective against ultraviolet radiation, right? So it actually protects our DNA. it's used for heat. We're now finding out that some birds use melanin in order to insulate. No
way.
Yeah. There's lots of really interesting things. It turns out it's actually resistant against radioactivity. So there's fungus that's growing in Chernobyl that's full of melanin. It's growing on the walls of the Chernobyl plant.
What?
And the melanin is protecting it from radiation. So there's all, and then there's color. So as you mentioned, structural color. And so you think of things like bird feathers. All bird feathers, a lot of animal skins, octopus skin, but also insects. This is all based on structural color. This is why actually, if you have a bird feather, like a peacock feather, like that thing will last 100 years and it will still have the same color, because most colors that thinking of paints, like that'll fade over time, right? But structural
dyes, like the shirts we're wearing, yeah.
Absolutely. So structural color is different, right? So structural color is basically, you think of, if you could put little posts down that are spaced apart exactly so that a wavelength of light actually can't make it through, right? So if they're somewhere on that nanometer scale, you can either block light or allow certain light to pass through, and other light will bounce back. And that's what structural color is, right? So it's basically filtering out certain wavelengths of light.
So this isn't blocking. This isn't, it's not like, when you talk about slits, my brain immediately goes diffraction. But
right.
This is not diffraction.
This is not diffraction.
This is slits that are blocking.
That are either blocking it or allowing it to go through.
By blocking, it must be absorbing.
No, if it's blocking, it's bouncing back at you.
It's bouncing back. Okay, cool.
Yeah. So that's what can give things, it can be green or yellow or red. And we also where these kind of really, shiny metallic types of colorings come from that.
Wow.
So yeah, melanin is, but melanin is a black polymer, right?
Yeah.
So what happens is that organisms put melanin in these things called melanosomes, and then those melanosomes get organized biologically into these patterns that are spaced apart exactly the right way, right? And again, evolution designed these things to be spaced apart by these exact spacings. We don't really know how that works.
But
it's
wild.
Pretty neat.
Yeah. Thank you for telling me that, because I saw somebody walking around with like a shirt that had the structure of melanin on it, and I was like, "What is that?" They're like, "It's melanin." I'm like,
no, you don't really know what.
I don't think you know like what's going on here.
Well, it was probably one of these cyclic precursors.
Yeah. Great. So for all my lovely people of color out there, there is so much more to your melanin that you don't even know.
Still don't know.
Yeah. Wow. We're just coming up on an hour, so I think we can call it.
All right.
Thank you so much for your time.
My pleasure.
It's been absolute.
I feel like we could have been here 2 or 3 hours and still had things to talk about. But hey, maybe there'll be a next time.
Yeah. There'll definitely be a next time. There'll definitely be.
You know where to find me.
Yeah, I do. I'm super happy that you are the chair of this department, and I'm like, I feel that it's going to be headed in a great direction.
Good. I'm really optimistic.
Sweet.
Cool. All right. Thanks a lot, Mashani.